Here we have two high induction coils. Turn that down if you can, Jack. The back one is the energized one. The front one is the one that receives the vibrations from the back one. The front one that receives the back one, the back coil that receives vibrations from the front one does so on a time distortion basis. The way to prove this is to put a neon across that load. And when we view the neon will view to us as a solid discharge, but the camera will record an on-off period of discharge due to the slip of the frequency involved with the high Q coil time distortion. Okay, what we're going to do now is turn it on without no neon load. I'm going to turn it on at 120 volts. Should be able to see the back coil receiving 80 some milliamps, 81.3 milliamps, and a front coil taking 40 milliamps from that vibration. Now we're going to go over here and show the load on that 40 milliamps. The 80 milliamps comes from a 12.8 Q coil, meaning every one of them 81 milliamps has 12.8 volts. The front coil receiving the vibrations, having 40 some milliamps, is a Q coil of 16 or so. And that means every milliamp has 16 volts. Now we're going to go and show the load here. The load placed on that second coil is a magnet and a neon in series across the voltage rise across the coil. When I turn this on, we're going to focus on the amperage drop and also the periodic on-off of the neon, showing the frequency difference from the time distortion exhibited by a sole receiver. Coming around here, we're going to get out here in front. We're going to hook that up. We also have a piece of foil at the midpoint discharge to hopefully stabilize it from an exterior plate source connected to antenna. And we should now be seeing this discharge. I'd like to move the camera to show the drop in conditions at the source. Now the sources went up to 89 milliamps and the secondary loads dropped to 21 milliamps. Now we're going to get a picture of the neon showing its cyclic discharge, which is continuous to our eyes. Let's get that in there. Okay, it's on. Off. On. Off. Now we want to compare this to something else to prove this point. On. Off. Now we're going to do something entirely different. I'm going to go back over here. We're going to vary the load on the neon. Now we're going to do an auto transformer thing. I'm going to do an auto transformer thing. That looks pretty good. We can see from there. Instead of having the neon magnet load strictly across the time distortion process, showing this slip of frequency. What we're going to do is we're going to make it an auto transformer, and we're going to hook it up to one source where the time is not distorted, the primary, and the other secondary connection is going to be left to where the time distortion occurs. This should change the cycle. Okay, we're trying to get through here. Gotta get it. We're at 89 input, 21 output on our milliamps of secondaries. Okay then. We're going to remove one of the inputs to the bottom plate going to the magnet, and we're going to put that at the midpoint of the primary coil. Well, we're trying here. We're at the midpoint. Our new conditions are 64 milliamps and 30 milliamps on the secondary. Now we need to turn the voltage down on this process so that we can get to the point where the camera captures the zero crossing point. We're at 120 volts. Let's go over here and show that. We're at 120 volts. We should be able to go down to about 50 volts. About 55 volts. No discharge. 60. We got a good discharge at 60 volts. 41 milliamps primary. 87. Only 8.6 milliamps on the secondary. Now let's look at the bulb activity. Here's the bulb activity. Let's see if we see a different cycle time. Off. Should be much slower. On. Off. On. Here we're connected across a non-distorted time voltage and a distorted time voltage. The frequency of the cycle should have changed. Off. On. We've gone through 3 cycles, and then we compare on review what these things are. The reason we say off and on is because sometimes when we put it off to YouTube, there's a discrepancy on the information because of the downsizing on of the YouTube when we put that thing on the YouTube. So here in the close, we're looking at our conditions. We got 60 volts in, 41 volts going through the back coil at 12.8 per milliamp, and we got 8.7 milliamps on the secondary response, and that's at 16 volts per milliamp. We're going to try to load this and put it on YouTube. Thank you.